Okay, in this video, we're working toward creating a slit scan image in a Pluto notebook. And so the packages I've loaded here are the VideoIO package, the PlutoUI package for some additional user interface elements in Pluto, and then the Julia images package. So the video is available on GitHub, my GitHub site, and it's this thing here. So let's use the resource function provided by VideoIO to take a look at this video. So we get a little player with some basic functionality. It's about a 28-second video. It's kind of a time lapse of clouds passing over the sky, shot from a bluff overlooking a river. And so that's where the file name comes from. So we have these kind of stationary elements. The trees in the background actually move a bit, but this collection of dead tree branches in the foreground are pretty stationary. Okay. So this allows us to view the video in our notebook, but not to really work with it in memory, not to get our hands on the internals of the color data and image data. So to do that, we'll use VideoIO. So I'll call this object BC for bluff clouds and use the load function with the same URL. It's a good idea here to suppress the output. And the reason for that is when I didn't do that before, didn't type the semicolon at the end of the line, what I got, in terms of display, it's fine. It's just shows you a very big collection of thumbnails, which I believe is one for each frame. But then I had trouble saving the notebook, and I also had trouble exporting to some of the formats, like creating a static web page to view the notebook contents, or doing this record function. And I think that the reason was because of not suppressing the output here. So let's examine this object a little bit. First, let's see what type of tells us about it. So it says that this is a vector with some kind of array containing image data, which is in a color format called RGB N0F8. How big is this array? So this will tell us the total number of frames. Okay, so there are 870 frames of video. And if you think about 30 frames per second playback, then dividing 870 by 30 gives 29, which is pretty close to the 28-second figures roughly reported by the video player. However, notice that this is actually a tuple containing just this one number, 870. So I want to pull out the integer value, so I'll just use an index of 1 here. It would also be a good idea to take a look at the first frame. So I'll call this first frame. All right, so we have this picture. And if I can get this thing to reset to the beginning, should be the same picture as up here, although the video player renderer, I think, is showing things a little bit darker maybe, but anyway, same image data. So how big is each frame? Let's capture the dimensions here, and I'll call this row size. So in other words, the number of rows, and call size. and I'll just use this first frame object. So it's each frame of video is a 360 by 640 image. So I've scaled this down spatially. It was originally shot as an HD video, I guess 1920 by 1080. Or if we mention rows first, then 1080 by 1920. So I've scaled it down by a factor of 3 in each dimension for an overall scale down of by a factor of 1/9, I guess we could say. And then I also sped it up. So it makes it a somewhat manageable size file that we're actually able to load the whole thing into memory using VideoIO. We can also check out the data type for the color information here. And so I want to give this a name, actually. I'll call it BC color type. And I'll just examine the first pixel. So the upper left pixel of this first frame. So as we saw up there, this is RGB N0F8. And so when I first saw that, I didn't know what N0F8 meant. This is one of the nice things we can do with this function, this feature of Pluto. Because I have the images package loaded, once I type out the name of this data type, I can just click here and get some information about it. So essentially this is a fixed point decimal, giving us a value from 0 to 1, and using 8 bits of data. So each channel, red, green, and blue, will have, for a given pixel, will have one of these numbers to tell the intensity for that channel, that color. All right, let's just delete that cell. Okay, so our first little project here will be to make a kind of scanner interface. So what I want is a slider and a black rectangle. And as I draw that slider thumb across the track to change the value of the highlighted column, I'll see this green scanner line moving across, and then it'll reveal a frame of video. So that's the goal for this first little interactive toy scanner. Okay, so then first what we'll need is a slider. And I'll call this variable the scan column. So scan call. I want the values of the variable to be in the range from 1 to call size. And I'll tell Pluto to show the value of the variable on the slider. Okay, so here's my slider, and the variable goes from 1 up to 640. You may notice that the slider here is not the usual slider that you get in Pluto. This sort of standard slider has a width that's about 20 or 25% of the overall cell width. So I modified that here using a little bit of CSS. Okay, so let's see. To actually create the display that we want, we'll need a little bit more code. So let's wrap this in a begin-end block. So first I want to define a rectangle. I'll call this black frame. And I'll use the zeros function with our color type. And then for the dimensions, what I want is the same as the dimensions of a frame of video. So I'll use the size function. But I need to use the splat operator to pull out those dimensions. And maybe we can just check what we have so far. Okay, so there's my black rectangle. Now I'll create a scan line. And for this I'll use the fill function. And I want to tell it what color, but I'll also specify the color type. So the color, I just want a fully saturated green. So 0, 1, 0. And for the dimensions, this is going to be, the number of rows should be the same as row size. And then just a single column. I won't execute the cell here to examine this, because if you have a one column image with a lot of rows, it'll, well, actually maybe even with just one row, it will magnify the size of that object for viewing, and it's not that useful. Okay, so to create the display, what I want is I want that scan line to be placed at the column specified by our slider value. So to the left of that, I want the columns 1 up to the scan column -1. I'll use the view function to construct this image without making a copy of the frame that I want to look at. And I'll just choose an arbitrary frame of video. And then after that comes the scan column, and then after that comes a view of this rectangle, the right-hand portion of it, from the scan column +1 up to call size. So we'll use the hcat function here. So for the video frame, I'll just choose, say, frame 230. So I want every row and columns from 1 up to scan call -1. Okay, then comes our scan line. And then a view of the black frame. Again, every row, but now from scan call +1 up to our call size. All right, so let me bring the slider back over to the left here. And then we'll try executing. All right, so this works. We have our toy scanner. and it's just revealing this one frame of video. So let's imagine that this is a kind of slit scan, the most basic slit scan that we can make, which is just a single frame of video. What I want to think about here is put this in the framework of a mathematical function. So this function takes a column number from the numbering of output columns. So that's our input to the function. And then the output to the function is a video frame from which we're going to source the column of pixels to fill in this column of our output image. So in other words, well, I've normalized the values here to the unit interval in each dimension, but our column numbers go from 1 to 640. Our video frames go from 1 to 870. So this says for column 1 of the output image, we want to take one single we want to take the column from one particular frame of video. But for column 2, we're taking our pixels from the exact same column. It's just a constant function. I didn't really use 0.2. You can try multiplying 0.2 times 870 if you want to. But anyway, so this is a constant function, and that's how you can think about what we get when we just take a single frame of video. Every pixel, in fact, in the whole image comes from one single frame. And the idea of slit scan is to loosen up a little bit, to not just work with a constant function here. So for example, another possibility would be that we use a different function, still working column by column, but what if we thought about the identity function? So in other words, the ith column of pixels in my output image should be drawn from the same column in the ith video frame. So the leftmost column, the first column, will come from the first frame. Right next to that, the second column will come from the second frame of video. The third column will come from the third frame of video, and so on. So here, of course, I have more video frames than columns in my output image here. So we have to maybe think about like truncating the number of video frames. Just instead imagine that we're going from 1 to 640. Then it really is the identity function. So, well, I suppose it would be the identity function if we changed this 1 to something greater, like 870 over 640. But anyway, so this is the kind of slit scan that I want to realize here. So the image, again, will be constructed column-wise, and that's not the only possibility. There are definitely other possibilities that we could choose. We can also kind of free up the correspondence from input columns and output columns. So for example, I've said here that I want the ith column of pixels in my output image to come from the ith column of pixels in the ith video frame. But that's not absolutely a fixed association. We could make a different choice there. And so, for example, what's called streak photography or finish line photography, you do something a little bit different, where every single column in the output image, let's say, comes from just one single column in the in the moving picture source, in the video source. All right, but let's try this. So what we'll get in our slit scan is that the things that are not really moving, so the tree, the kind of dead tree branches in the foreground, and more or less the trees that are in the background, those things will kind of be copied in place in our output image because they don't move too much. But the clouds are very dynamic, and so we'll get some interesting effects with the clouds. All right, so I want to make a scanner interface again, but I want this one to be a little bit different. So what we'll have this time is the slit scan image will be formed on the left as we draw the slider across. The border, the boundary, will still be a green column of pixels. But to the right, what we'll have is the frames of video successively played as we advance the value of the slider. So, so over here, essentially, we'll see video playback to the right of our scanning column. And so the scan line will be kind of, will appear to freeze pixels from the video playback into the image. However, I want to modify that just a little bit by washing out the video signal, just to kind of more clearly distinguish it from the slit scan. And so I'll take the mean, the arithmetic mean of the video signal and a white rectangle. All right, so let's try to realize this. So here, I want to start with thinking about the video playback. And so I'll call this variable frame number. I want to use the clamp function. Here's where our function would go. Okay, but I'm just going to use the identity function. So yeah, so this is going to be the value of the slider. I forgot to put the slider in, so I'll do that next. But let's say that we call the value of the slider. Let's see, we used scan call up above, so I'm going to have a new slider here. I'll call this one highlight call. And I want to make sure that my frame number is the number of an actual frame of my BC array, so my video signal. So we'll say from 1 up to total frames. Again, it's not really necessary for this particular function because we're only going to get values from 1 to 640. So definitely the clamp function will just be the identity on that set of values. But if we did try some kind of more exotic function later on, where maybe we end up getting video values, video frame values that are outside of that range, it'd be nice to ensure that we don't get an error from that. So let me go ahead and make the slider. And so this variable is highlight call. Again, from 1 to call size. And I want to show the value. Okay, so then the video frame to be displayed will be BC indexed by frame number. then our white frame this will look similar to the black frame, but we'll just use the ones function instead of the zeros function. So we want to use BC color type and then the dimensions of the first frame. Maybe we can check our display, check and see what this white frame looks like. All right, so it seems like it's about the right size. It's hard to really see anything. Okay, so here's where we create the slit scan. Let's call this slit scan frame. And I'm going to use an iterator here. So what I want to do is to take a column from BC, so I'll name this variable, let's say scanning call. This is actually the frame number reference, but again, I want the frame number to be the same as the column number. And then this is the extracting that column of pixels, every row in this particular column. So the slit scan part of the image of our scanner image, the slit scan is going to be to the left of our highlight call. So from 1 to highlight call -1. All right, so then let's put together these elements. I haven't defined the green scanning column here, the scan line, but I'll just refer to it from this cell. And then a view of our white frame. What we want to take is from highlight call +1 up to the call size. So every row these columns. Right, this is not what I intended to display over here. Okay, but you can see what the slit scan is looking like. Let me hide that for the moment. That didn't seem to work. All right. What I really meant to do was to take an average of the white frame and and the vid frame. So let's call this, this is maybe a little bit of an awkward variable, but all right, so I want to take an average. So 0.5 times vid frame plus 0.5 times white frame. But with these float operations, then I'll be converting everything to floats. And so I want to stick with, again, with BC color type. All right, so now let's change this to vid frame display. And I'll try again here. Okay, so there I have my washed out video and my green scanning column. I'm going to go ahead and hide the code for that slider. And let's try viewing the slit scan. Okay, so here's our first slit scan image. What I notice as I draw this across is that this is really not optimal code. And the reason is because the whole slit scan is recalculated every time that the slider value updates the value of the variable. So what would be better is to create the full frame slit scan initially, and then maybe even in a different cell, and then just have the calculations here only work with what we're actually displaying in our scanner interface. But in any case, we do have a slit scan image. So let's take a look at it for a minute here. You notice that the clouds have a very different shape than the clouds that we saw before. So this looks like kind of threatening weather. Not such puffy, rounded clouds like what we had here. And they're kind of swept up and to the right. So if we look at the way that the image is formed, and think about the motion of the clouds in the video, you can see over here the clouds are moving to the right and kind of moving up. And so that motion, in a sense, is captured in this one single frame by the slit scan process. This cloud here also gets very elongated. The closer the clouds are to us, the faster their apparent motion in the sky. And so the clouds in the distance, they don't seem to be really stretched out in that way. But the ones that are closer, the apparent velocity is higher. And so it looks more like they're stretched out. The other, one of the other really noticeable features about this image is these sudden jumps in brightness in the image, here and here and here. And so this comes from the automatic brightness compensation in the camera. If we had a way of disabling that, we might be able to get a slit scan image that's a little bit more continuous. When you're playing back video, at the instant when that occurs, you sort of notice that jump in brightness. It either goes up or it goes down a bit. And then your perception, or, well, your observation kind of gets acclimated to the new brightness level. And it's not a phenomenon that persists over time, but here we can kind of see it because we have a record of this changing scene over time. All right, so what else can we do here? It would be interesting to try a different function. So for example, I've used the identity function here so that, again, the ith column of pixels is copied from the ith column of the ith frame of our video source. What if we switch this around and kind of reverse the process? So in other words, the leftmost column of pixels come from later in the video. And as we advance across the image frame from column 1 up to column 640, we're rewinding the video, so we're playing backwards. So maybe, for example, we start with the last frame and then work our way back in the direction of the beginning of the video. Well, let's try that here. This time I'll leave off the scanning interface and I'll just try creating the scan image. So I'll call this image 2. And I want to use something similar to this. So I'll just copy and paste. But I want to do the whole thing all at once. So I'll change this to call size. And I don't want to use the identity function. So the frame of video from which I'll take this column of pixels, let's say that we start at the end. So this is total frames. And then we subtract scanning call. So really, this means that the first column of pixels would be 870 minus 1. You could add 1 if you want to truly begin at the end of the video, the very last frame, but I don't mind having shift by 1 frame. And also you could be a little bit more cautious here to make sure that you don't get some index that's out of bounds. But I know that I'm safe with this for the moment. Since this is just a notebook, I won't worry about that issue. So what happens if we just try this line of code? Okay, we get something maybe a little bit unexpected. It's somehow describing in text what this thing looks like. And that's not quite what I want. I think that, yeah, so this tells me it's a 640 by 1 matrix. What I want is a 640 by 360 matrix of color data. So the thing I believe what I need to do here is to use the splat operator here. And there we go. Okay, so this is our image 2. And notice the difference in the way that the clouds look. This time the clouds, instead of being elongated and stretched out upwards and to the right, they are sort of horizontally compressed. These kind of cloud heads look a bit taller. All right, so this is another way that we could create this slit scan, and there are many different things that we could do. Notice that the sort of stationary elements, the dead tree branches in the foreground and the trees in the background, they are not totally stationary. And so if we had higher resolution here and we looked carefully, we might be able to see a little bit of strangeness, let's say some kind of blurring or shakiness in the trees in the distance. But basically, those dark colored elements in our image give us this frame of reference. And doing different kinds of slit scan functions, this sort of function, we can get really wildly varying patterns in the clouds, but still have it look essentially like a kind of normal scene because of these stationary elements. Some other things that you might try doing, one would be to create a slit scan that's operating row by row instead of column by column. That could produce some interesting results. Another interactive thing that you could do would be to create an offset. So we started all the way at the end of the video, but if I change this to a different value, I'll get a different image. So for example, what if I said, let's see, so the number of columns that we have is 640. So any value between 640 and 870, or even really 871, should be fine. Wait, if I'm subtracting scanning call, then actually I can only go down to 641 because the minimum value of that is 1. Sorry, the maximum value is 640. And if I went 640 minus 640, I would get 0. Anyway, what if I started instead at, let's say, 750? All right, so then I get just a different looking slit scan. Still kind of see horizontally squeezed clouds, but it's just from a different place in the video, or a different interval of time in the video, really. All right, so the last thing I want to look at here is how do we save an image from the notebook? And this is pretty straightforward, except one thing to keep in mind is a notebook is reactive, so we don't want to keep a live cell with a save operation when the data that we're saving may be getting changed by our interactions with other cells in the notebook. So a good idea is to create the cell, execute it to save the file, maybe check that the file has been saved, but then after that to disable the cell. So let's try this. Let's say that we save. Actually, I first need a file name. So let me maybe do this again. And I'll call this just image file name. And I've saved a few of these before, so let me call this one new slit scan. All right, so then it's just save. I want to tell it where to save and then what to save. So I'll save this one, image 2. And when I execute this, the file is saved and I get an output value, a return value. So I can actually check from within the notebook that it was successful if I use the resource function. Actually, I want to use local resource because this is not on the web. Okay, and there it is. So again, best practice here is probably to disable the cell. Oh, I see. When I do that, it disables this one also because of the reference to image file name. So if you didn't want that to happen, you could always change that to a literal. What happened here? I didn't copy the quotes. Okay. So I would say try things out. Try some different methods of creating a slit scan. It's a lot of fun. So thanks for watching. If you found this video useful or interesting, please consider leaving a comment or sharing a link to the video.